Welcome to Electrical Engineering 362, Electromechanical Energy Conversion. This is Lecture 2 of Module 2, Magnetic Circuit Analysis. I'd like to first of all review what we discussed in our last lecture. We talked about Ampere's law, which was the enclosed current equal, and what we've started using is we have a number of turns times the current. That would be the same thing as enclosed current, and that being equal to the line integral of the H magnetic field intensity dot dl. We talked about how in this class for most of the time we're going to be working with scalar quantities, not vectors. For me, it's confusing when I was in your position, distinguishing between scalars, phasors, vectors, and all that. And I've tried to clear that up a little bit in our first lectures. But, you know, when you take your electromagnetics classes, a lot of times they're talking about phasors. You don't realize it, so phasor is a phase vector. It has, in the electromagnetics world, your voltages and your currents have both temporal, time, and spatial position dependencies, and it's because of the frequencies at which electromagnetics is studied. It's these higher than radio frequency. Well, we're dealing with frequencies that are anywhere from DC to 60 hertz, and so when it's going to be very clear, and when I talk about what a scalar is an instantaneous value at a given point of time and space. And so that would be sometimes if you're using three-dimensional space, then you might have your H would have this little symbol over it, meaning that that it has positional properties in three domains, right? X, Y, Z, for example. For the most part, we can constrain it to the X, the Y, or the Z, and so a lot of times you say the H there's an HX, an HY, and an HZ. Well, we are usually only going to be working with one of these guys, so we can just drop the little subletter and just look at the picture and think of it that way. And so what I found this picture on the internet, which I really like because it shows you how we introduced the Ampere's law being applied around a single wire, just like where I highlighted, and how we also had a coil of wires and how they all combine to give us this H going in this direction. Instead of the H going around one wire, it's going around all the wires. So I like to think of this I enclosed as the current that's enclosed by the magnetic field lines that we're showing here. Now the definition of H could be any point inside space here. So if I were to, let's say, just highlight one line in the middle of the coil, I could calculate the H at that point. And so H is a value at a given point in space. I told you all for an entire period putting the H in the center of the core, and notice this doggone line is offset. It just confused students. Well, I erased the doggone line there, okay? Just so ignore the line at the moment. We'll talk about this in a moment. Ignore Fitzgerald Kingsley's line. I don't know why he offset it. But in air, we also found out that we can find another quantity which we call flux density, and that would be B. And often, when you're doing electromagnetics, you also have, Bx, By, Bz. But again, we're really only looking at one or the other. The difference between B and H is simply a multiplication times again a scalar quantity. So we have this expression here, and we're talking about in the air. The flux density in the air is related to the magnetic field intensity by mu naught 4 pi times 10 to the negative 7th Henry per meters. We could apply the Gauss's law to a lot of different scenarios, but it's a lot easier to think about it being applied to this, something like this core structure. And what the core does is it enables you to concentrate the magnetic flux lines inside of the material, as opposed to them going all over the place, like we're seeing in this picture here, right? You got these different lines in the air, and if we can constrain those magnetic flux lines inside of the core material, it gives us a very straightforward way of looking at this. And we're going to talk a little bit more. We were at the end of the period talking about why we use cores. One other thing though, I mentioned flux. What is flux? The flux would have this symbol here, and it is the integration of the orthogonal component of the B across a surface area. And so there's a kind of shorthand way of writing it, but really what you have, if you look at the air, for example, and I tried to find a good picture of this online, but I couldn't, of a flux tube. But you can think of, you could imagine drawing little lines around these flux lines, and if we define an area that we're intersecting, that's kind of what a flux tube looks like. So if you were looking at this problem in air, it would look like that, and this is an area at some position, some point in space. And so we defined, let's say, the H as being in the center of the coil, and we say, okay, I'm going to pick one of these lines and say that's where I'm evaluating my H. Well, that line in the center comes back around. It's not really giving. Okay, so here we go right here. So there's the H, and that would also be the B if you just multiplied it times mu naught. And if it's hitting the normal surface area here, if you integrate over that surface area, you would get the flux. And so really the flux in the flux is the B times the area, and so B is a density. And as I told you last time in our lecture that the flux had the units of Webers, or this WB, your B would have the units of Webers per meter squared. It's a density. And then we introduced Gauss's law, which would say if I were to create a closed surface area, so let's take this flux tube idea here and let's create two surfaces and close the boundary between them, then the flux coming in, so let's call this flux 1, and the flux going out would be equal to each other. That's really what Gauss's law is saying. So Gauss's law is saying mathematically that the closed surface area integral of B dot ds equals 0. And that really also means that the flux in, flux 1, is going to be equal to flux 2, the flux coming out of the surface area. Okay, so this was just a quick overview of those first two laws that we are going to be using a lot in this class. In this lecture, we will talk about BH curves, the magnetic saturation of cores, units that are used typically in magnetic quantities, both SI units and CGS units. We will talk about the concept of magnetomotive force, or MMF, what it is. We will also introduce reluctance in a magnetic core or an air gap. And we will introduce the magnetic circuit. First for a ungapped core, a simple core structure, and then we will introduce an air gap into the simple core structure and derive the magnetic circuit for the gapped core structure. Alright, so we also talked about impressing a magnetic field onto a core. And here's my better picture that I doctored up, and I want to show you again. I've got this number of turns wound around this magnetic core, and I'm also going to draw this line because we talked about it. This is right in the middle of the core. In the last lecture I called it L mean because it would be the averaged line, but we're going to call this something else now. So I had L mean, but we'll just say this is LC, the length, mean length of the core, magnetic field intensity through the core, LC. And so H you can imagine as being the same on every point along this line, and then we're pointing the line in this direction, which would come from right hand rule because I've got my thumb pointing in the direction of the H, and I'm going to have my fingers in the direction of the current in this case, and that points the direction that it's going to travel. Now the magnetic material here, which is a ferromagnetic material, that we're working with has inside of it domains. It's like a crystalline structure, and these domains have magnetic dipole moments inside of them. And I found online maybe a better picture, not the best picture. I like to draw these little arrows like this. That's how I was drawing them before. But you can see that if I have I equals 0, so I've not applied any current to that core, and it's really never seen any current ever, okay? Let's assume hypothetically that's the case. You've got these randomized directions of these magnetic moments. But as you start to, let's say, increase the current, I can say I'm going to go to some current level I1, you're going to start to push. And what I'm showing here too, really quick, is it's kind of like I lifted a section of this core out, and that's what I'm looking at right there. And so at I1 I start to push because I've got my current going in that direction. You can see the arrows are starting to go and point generally in that direction. And then at some point they're all lined up at a higher current. They all line up in the direction of the H, and the H also corresponds to the direction of the flux that's in the core. So the other thing is that the H that is inside of the core, I'm not going to talk about it in terms of H, I'm going to talk about it in terms of B instead. So there's a magnetic flux density inside of the core, B. And for now I'm going to call this B sub C, but we're going to eventually be dropping these subscripts. And it consists of a B naught and a B induction. So this B naught is the flux density in the air, and the B induction is what's induced into the core. So really what happens, what I'm saying is that the space that the winding is wound around is both core and air. Core and air both occupy that space simultaneously. So if I can think of it in that way, then the B naught is mu naught H. And the B induction, we're going to say, is mu naught times some magnetizing field intensity, where we've magnetized the core. And now what I'm going to do is I'm going to define M, the magnetized field intensity, as being equal to this chi symbol times H in the core. I'm also going to go up here and I'm going to put the little C subscript on the H right there. Okay, so I'm talking about this H. And the M, this little expression here, could plug in for that M value there. So this chi is defined as the magnetic susceptibility of the material. It's how susceptible is the material to being magnetized. That's what it represents. So I'm going to plug this into that expression and let's work out the flux density in the core. It's mu naught times the field intensity in the core plus mu naught times chi times the field intensity in the core. And if I pull out the mu naught, then, and I'm going to put the HC over on this side, I end up with this expression in the middle, 1 plus chi. Mu naught 1 plus chi HC. And what we do is we define this thing here, this 1 plus chi, as mu relative. And it's a unitless quantity. It has no units. It's just a little multiplier times the mu naught. And so we can say the flux density in the core is actually mu naught mu r HC. Typically, we also would combine these and just call that mu. So if I dropped the subscript C, this is the way you'll typically see this written. B is equal to mu, mu times H. Just give me a minute. I'm going to clean this up quickly.
Times or dotted with H?
It's times. We don't have any vectors, okay? So I don't like to put little stars all over the place either, and I could even argue that a dot and a time with scalars the same thing. Is that okay? Does it make sense? We don't have vectors, so you don't do dot products, and you don't do curls, you don't do cross products, we don't do any of that really ugly stuff. Sorry about that if anybody's disappointed, but so if I put a little dot, I just mean multiplied.
No, not really. I'm not
You're okay?
disappointed.
Okay, you're not good. All right. Okay, I don't want somebody to say, oh, Kusner doesn't do dot products, his class sucks, blah, blah, blah. Okay, anyways, so mu is mu naught mu r. If this was an electromagnetics course, even that mu would, I mean, if this was a hardcore electromagnetics, you would have real reactive and quantities in that mu, and your H's and your B's would be dimensional. Thankfully, we don't have to worry about that in this class. Okay, so what really this means is the magnetic, when you use a core, why do you want to have a core? I would like to call it a magnetic amplifier. And what you're going to learn in this class is that we're trying to use electromagnetics to do things for us, to do work, really. And the B is the work. So B's the work. That's what you're getting out of it. And the H is what you're putting into it, the current. Because H is, as we went through last time, Ampere's law has a proportionality with the current. And so this is what you have to put into it. And usually there's losses that come along with that the more you have to put in. So if you can put less H in and get more B out, you've got a better situation. So we've defined the mu as mu r, mu naught, and we had derived the mu r from this magnetic susceptibility, 1 plus chi. If you have, for a ferrous material, if you're unsaturated, that means that, actually I haven't introduced what unsaturated means yet. Let's just wait a second on that. We're going to come back to this. I'm going to talk about this magnetic amplifier concept first. Okay, so there's two axes. I'm going to define the x-axis as B, and the y-axis is B, and the x-axis as H. And I'm going to use the units, ampere turns per meter. One quick thing about the units on B. We said that B is Webers per meter squared, but there's a nice shorthand way of writing that, and we use something called a Tesla, or T. And that is the SI, so everything is now in SI units. And we'll come back to some different units again in a moment. So this is really helpful to see. For so many turns, I put in a certain amount of ampere and I get what's on this x-axis. So I got 200, 400, 600, 800, 1,000, and so on. Now, if I were to consider the flux density in air, it would be B is equal to mu naught times H. And what I would end up getting in Teslas is 0.25 Tesla, 0.5 Tesla, 0.75, and 1 Tesla. So these intersecting points we're going to talk about here. At 200, that point right there is the flux density in air. At 400, I can get to 0.5. I'm going to move these points a little bit, I think. At 600.75, and I can get 1 Tesla. It's a straight line. It's linear, right? So basically you're looking at a XY linear plot, a line. Now, and the slope of this line, the slope is mu naught. Inside of the core, let's use a different color here. What would I get? Well, let's say we've got this mu relative that's going to multiply times that. So in the core, I've got B mu relative mu naught H. And it depends on the core material, but what's going to happen is because of this multiplier, and it's quite a large number, I'm going to be at a significantly higher level of flux density. Now what I want to take this back and coordinate it back or correlate it back to these this magnetized condition and these dipoles in the magnetic domains, because we would also imagine that as we start to put more current into this material, we're going to start to line up the magnetic domains. So what does that do to this BH curve? What will happen is that as I put more current in, I'm going to get less effect in my B. And so in this region here, this is the it's really unmagnetized. I still kind of have a randomization of those magnetic dipole moments, and it's typically referred to as the linear region. And what that means is that the mu r is going to be some value, and typical mu r's for ferrous material are anywhere in the range from around 2,000 to 200,000. I mean, it's in this kind of range. It's a pretty big number. And you know, I don't know if it could be 1,000 too. It's just what are the typical values of the mu r. But when you get to this point here, we're actually in this partially magnetized condition. And so we typically refer to this region here where it starts to not become linear as the knee of the curve. And it's really where the curve starts to bend. And there's really kind of a deflection point. That's the exact knee right there. In some magnetic materials, it's going to be a little more pronounced than others. And you're starting to really line up the domains. And then if you keep putting current in, you get less and less impact. And so you're in this region here. This is called the saturated region, or the magnetized region. So you're fully magnetized, and it would follow then down here in this unmagnetized. I could call this the unsaturated region, and it's the linear region. So if I'm unsaturated, I'm linear, and typically we think about us in this region in relative senses. The mu r approaches infinity. It's a very, very big number. But as we get up here into this saturated region, the mu r starts to approach unity. And you could say, well, I could put so much current into this that it just looks like I have air again. It'd be pointless to do that. You'd just be burning up a lot of heat in your wires to do that. So there's really an optimal point at which you want to typically operate, which should be right around this knee, where you're getting the best maximum benefit of your material. Any questions about that? Pretty clear? This
Yeah, that makes sense. It's kind of like a saturation curve on a transistor, right?
yeah, it's very similar.
What it operates like. So.
Yep, operates just like transistors in that standpoint. It's like an amplifier. Now what this curve here, and I'm using this green color here, I'm going to say that the green is a ferromagnetic material. Typically, this is like silicon steel. It's a typical type of material that you would be encountering there. And let me shrink these down a little bit here. If I had what's called a ferrimagnetic material, I'll use a different color for that. Ferrimagnetic. And a very good example of a ferrimagnetic material is a ferrite. And it's usually we'll go into what these differences are, but this is typically a powdered iron that's compressed. And the ferromagnetic material is typically, not in all cases, there's some things that are somewhere in between, but is a laminated steel. And we'll go into why you have this with these materials. But the ferrimagnetic curve would look more like this. It would typically be steeper and saturate sooner and be much flatter. So there's a ferrimagnetic material. The nice thing about ferri versus ferro is the ferrimagnetic materials can handle higher frequencies and of AC excitation, and so we'll talk about that as we discuss core losses, and that's the benefit of ferrimagnetic material. So this picture here shows the three regions of the B curve, which is this blue curve right here. This is mu r. And then the B is this other axis here. The blue is the B in Teslas. Okay, so let's talk about units for a moment. Typical units. And it's important because I don't know if any of you would go up on Canvas, you'll see that I have posted a lot of supplementary materials, including a lot of core material data sheets for different types of cores. And so you're not always going to get them in the units that we like to work with. And so the B unit is Tesla. Tesla's also the same as Webers per meter squared, and we will introduce, once we talk about Faraday's law, another way of describing, or another unit for B, which is all in SI units. But I think this is the CGS units. So these are SI units. You go back to your physics classes in your physics textbooks, right? Centimeter, gram, seconds, CGS units. The B is given in Gauss, or more typically kilogauss, or kg, and that is the most often common unit that you find in data sheets for materials. The conversion factor between Tesla and Gauss, 1 Tesla is equal to 10 kilogauss. And then, as I talked about last time, the H in the SI units is ampere turns per meter. 1 Oersted there's no T is equal to 1000 over 4 pi. Okay, so we've talked about SI units, CGS units. Now there is one other one. When I learned magnetics, I was taught that I should be able to be very fluid and going between units. And so the older one, the old school people like me, like British units also, right? So we like inches, feet, right? And all that kind of stuff. So let me go back and give you flux. The flux is Weber's, WB. I'm not really sure what it is in CGS. That's the SI unit. In British unit, the flux is lines. So yeah, very straightforward, right? You've got it's like you have flux lines. You got a coil, it's producing flux lines. You got your north and your south. And they say, okay, I got this so many lines, and that would be the British unit. I don't know the conversion factor. The B ends up becoming lines per square inch. I can't remember the conversion factors, but this is just kind of an FYI. Okay, any questions so far on that stuff?
Not at the moment.
Okay, let's talk about, and anybody other than Sean, be sure to feel free that you can speak up. I see we've lost 6 people in the class. Hopefully they don't fall behind. I'm going to talk about this structure. Right now I've got some dimensionalization in there because I'm going to give you an example. But before we do that, this picture is a little bit different, and you need to be able to twist your mind around these things a little bit. So notice I've got the current, the copper wire, but look, it's going the other direction. It's wrapping around the back. So what's that going to do? So your current I is coming in here through the copper wire, and it's going to give you the flux in the opposite direction. See this little arrow right here? It's going that way now. So you can go in different directions, depends on how you wrap around the copper wire and the current direction and what direction it's going. And right now I'm saying I've just got a current at one current level. It's a positive current, right? The I greater than 0. It could be a DC quantity or an instantaneous positive quantity, DC positive or instantaneous. The current enclosed is equal to H line integral dot dl. And the line that we're talking about is this single line. That's what we were calling LC. It would be the line in the middle of this core. So N times I ends up being H times whatever LC is. there's another term that we're going to use for the n times I gave you the name of it in our last lecture: magnetomotive force, or MMF. So this is a very important term to remember. The symbol for MMF is F, and F is equal to N times I. So we could rewrite Ampere's law for this rectangular core structure as F equals HLC. Now let's take this a little bit further. We've introduced this term called MMF. That's equal to N times I. And for this structure here, I'm going to copy this, put it here. The length of the core is really the length of this line in the middle of the core, and so F is equal to the H value times L C. We also know that H is equal to B divided by mu naught. So remember, we got this expression. B is, it's not mu naught, but mu, because we're in the core now. So H is B over mu. Just rearranging that expression. So let's take this and plug that into there. F now is equal to B times LC over mu. We also know that the B, and I'm going to use a little subscript C right now, so we're talking about what is the flux density in the core. Well, if I wanted to find the flux density in the core, I would find the cross-sectional area that the flux, and this is the flux right here, he's calling it phi sub m in this picture. I don't like the sub m, so we're just gonna ignore it. Okay, just get rid of that. There's our phi. There's our m. I'm going to ignore this voltage. We haven't done Faraday's law yet. And I like to write scalars as small letters, not capital letters. Okay, so the B times, and this is the length of the core, and then the cross-sectional area, I'm going to call this area of the core. So B times the area of the core is equal to the flux that's in the core. Now that we just have a very simple core structure, and I'm going to introduce much more complicated core structures. But in this core structure, the AC is the same everywhere for this core at all positions. So I could put the area right here and I'd get the same area. And in this case, and we want to be a little bit fluid about what we call things, we're using B right now as the dimension in this z-axis here, and this x-axis A. So the area of the core is B times A. So the flux is equal to the B that's in the core times A times B for this specific case here. So if I know that, then I'm going to shrink this down a little bit so we can add more to the discussion. I can plug in the flux for B. So I can also say, well, what is B in terms of flux? It's equal to the flux divided by the area of the core. And I can plug this B into here. And now I have a MMF expression that is equal to the flux times the length of the core divided by mu and the area of the core. What's significant here is we're going to introduce magnetic circuits, and there's a lot of analogies between the magnetic world and the electrical world, and here's the first one. The analogy is that this term right here can be isolated out and expressed as something that we call a reluctance. And the reluctance is kind of like a magnetic resistance. And the flux is like a magnetic current. It flows. And therefore the F would be like a magnetic potential. And so we have the makings now of what we would call a magnetic circuit. So I can rewrite F is equal to the flux times the reluctance. And the reluctance has the units of what are called Siemens. So if that's the case, then there is an electrical analogy to magnetic systems. And that electrical analogy uses, in electrical systems, we use circuits. And so we can basically say that the F is analogous to a voltage in the electrical world. We can say that the flux is analogous to current in the electrical world, and the reluctance is analogous to resistance in the electrical world. And we kind of have a magnetic Ohm's law here, okay? But it's not Ohm's, it's Siemens, which basically says F equals flux times the reluctance. If that's the case, we could actually draw a magnetic circuit for this core structure that we've been talking about. Just like this, where this is F, this is flux, and this is the reluctance of the core. And the reluctance of the core is equal to the length of the core over the permeability of the core and the area, cross-sectional area of the core. Any questions about that?
Are you going to give an example in the future of how to use that
Oh yeah.
in a more practical way?
Yep.
All right, cool.
So let's start with one right now. Here is the same core that we were talking about, and we've cut a gap in the core. So we've actually added a gap to the core. And what we've done by doing this is that we've changed the permeability of the core in that area. And so if I can look at this system, I can say, let's look at the core. Everywhere in the core, this is a simple core. It has a dimension A, or what was it, B and A, I think. Yeah. B, and this is dimension A. That's the area of the core. A times B. Everywhere in this core, everywhere along that core, I got the same dimension. So the reluctance of the core is equal to the length of the core, which is the mean length in the middle of this structure right here, divided by mu and the area of the core. What I've done is I've cut out a little section of the core, and we're going to zoom in on this little section here. We've got flux lines that are flowing through this core. Notice in this direction, this case, I've wrapped the wire around the front side, so my arrows are pointing in this direction. Gauss's law tells me that the flux on one side of the gap is going to be equal to the flux on the other side of the gap. But what about the flux inside of the gap? Well, what's going to happen is we're not going to be 100% constrained by the core once we get into the air. So the flux is going to bridge this gap, and it's going to fringe out. And so what you get is you're going to get a fringing effect when you hit the gap. And if I were to draw a line in the middle of that gap, it's kind of like the core. This was the dimension A, right? This line here is greater than A, the dimension. Maybe I can call it A prime. And if I were to turn, I'm looking at this surface. If I were to look at this surface here, I'd see the same thing. The flux lines would come down and they'd fringe out. And so this would have been B. And then I've got this B prime that's going to be greater than B. So what I can say is that I have this is a lot of everything we're doing when we look at these magnetic components is approximations, because if to do this exactly, we'd have to have finite element analysis software. So this is an approximation, but the area of the gap, I'm going to say, is approximate. It's equal to A prime times B prime. And what's the length of the gap? Well, we know that the length of the core was this entire length here. The length of the gap is how long we have to cross across here. So that's the length of the gap. So the reluctance of the gap is equal to the length of the gap, and we're in the air, we're not in the core, so it's mu naught times area of the gap. So I have two reluctances now, and I could actually write a magnetic circuit here. So here's my MMF that I'm applying. It's like a voltage.
If you don't mind, a quick
Sure.
question.
Sure.
So you said length of the gap, that's mean as the flux crossing to the from the other portion to the other portion through the gap, or as
Yeah.
oh, I don't know exactly where is the
It,
length of the gap.
it's like this. Here's the structure that we zoomed in on. It's the physical cut distance that I cut here. LG. How much did I cut out of the core to make the gap? That's what it is. Does that make sense? It's
Yes,
how
thank
how wide is that gap that and the flux is going to travel across it. So it's really a very physically measurable thing. You could take some calipers or something and measure it. It's usually pretty small. But I can write now a magnetic circuit here. This is F equals Ni. There's a reluctance of the core. It's the same everywhere in the core of this core structure. And there's a reluctance of the gap. So they're in series with each other. And here's the flux in the core. The flux, by Gauss's law, is the same everywhere in this core structure. And essentially I've got an MMF drop across the gap, and I have an MMF drop across the core. I've got this little thing I taught you called Ampere's law. It's actually analogous to Kirchhoff's voltage law. And it basically says that the F that's applied is equal to the F of the core plus the F of the gap. And that is what Ampere's law would tell me if I were to apply it essentially in its integral form, which is n times I equals h dot dl. It's going to give me this expression right here. So I think we need to end right there, but what we've been able to do is we have been able to apply a magnetic circuit to begin to understand what's happening in this structure. And it's also important to note that the area of the gap is greater than the area of the core because of fringing.